We're continuing on here with chapter 14. So last time we were talking something about chemistry. I think it involved acids and bases. So last time we talked about kind of calculating the pH of really strong acids and bases. And really in those cases, because they are strong acids and strong bases, they will 100% dissociate in solution. Which means essentially in most cases, the acid concentration will give you directly the H plus concentration. Remember though, for the base, it will give you the OH minus concentration. That allows you to go directly into the pH there for a strong acid. You will need to do a little bit more work there, probably POH first and then to the pH to get it for a strong base. Remember, you do need to watch out for as well if either the H plus or the OH minus doesn't break apart into a one-to-one relationship, like the example I think we did. You need to sort of adjust your concentration accordingly. I think we had like 2 hydroxides there with calcium hydroxide. So you want to make sure that you do get the correct hydroxide concentration. We then kind of talked about weak acids. And weak acids are weak electrolytes. And because they are weak acids, they will set up an equilibrium, and we can write an equilibrium constant for it, which is known as the Ka value. And the Ka expression is basically the equilibrium constant for weak acids. It is the same sort of equilibrium that we've talked about previously, products over reactants. And to solve these type of problems for sort of what the pH is of that solution, you do need to do an ice table again, because it's an equilibrium. It's not going to 100% dissociate. Actually, most of it will stay together. So you need to do your ice table here, molarity, zeros, X's, all that good stuff. Here you would solve for X. And once again, it really is just an equilibrium problem. So you can make your assumption, which a lot of times will work in a good amount of times. You could also obviously do the quadratic or any other way to solve these guys. When you do solve these guys, that will equal the H plus concentration pretty much for X. And then you could go into the pH equation there to get to your pH. So weak acid is a little bit different. You do have to sort of do an ice table. And again, you could do all the normal sort of assumptions. And remember that you do need to check them, as we saw, I think, towards the end last time. Even though it's the same reaction, the difference in the concentrations of, say, when we started with 0.05 versus 0.5 in the first example, the 0.05 was too large of a change to do the assumption. So again, make sure you're still in the habit of checking those assumptions. Any questions on any of that? All right, so let's try another one here. Let's calculate the H plus, and why don't we add pH to this as well? What is the pH and the H plus concentration of 0.01 molar HCN, Ka value there? I'm assuming one of those answers might be right. Okay, let's take a look and see how you're doing. So once again, we see the Ka value. We definitely know this is going to be a weak acid. So we should probably ice table it up here. So our HCN going to break apart into H plus and Cn minus. Our Ka in this case would be our H plus times our Cn minus divided by our HCN, and that's going to equal 6.2 times 10 to the minus 10. We're going to initially start here with 0.0100. Change minus x plus x plus x means at equilibrium 0.01 minus x, x, and x. So like normal here, we're going to put this into our expression. And if we do that there, that's going to give us x squared divided by 0.01 minus x equals 6.2 times 10 to the minus 10. I'm going to assume x is equal to 0. That gives me x squared divided by 0.01 equals 6.2 times 10 to the minus 10. as my K value is a small value, so I could do that. We'll do 6.2 to the minus 10. We're going to multiply the 0.01 to the other side, and we're also going to take the square root of it. And we will end up, when we do all that, once again, multiplying that and then taking the square root, we get, call it 2.49 times 10. 1, 2, 3, 4, 5, 6, minus 6. Once again here, because we did make the assumption, we do want to check it. And to check it, we're just going to divide it by what our initial concentration was, times it by 100. And if we do that, what we will see is we're like 0.02%. So the check here is good. It's like 0.02%. That means that this X value that we got is what we need here for our H plus concentration. So our concentration of H plus in this case would equal basically 2.5 times 10 to the minus 6 molar. Looks like that's going to be number 2. That also would then allow us to calculate that into our pH, which in this case looks like it would be 5.60 in this case. Yeah. Any questions on any part of that there? Yeah. Well, you could always try anytime the K value is relatively small. So technically, anytime you have a K value with like a negative exponent, you could give it a try. Again, in a good number of cases, it'll probably be okay, but you definitely should check it, as we saw in the last problem and some other problems. It may not always work. So again, the alternative to that is you don't have to make the assumption. You could just roll through the quadratic if you want to roll that way, and you should get the same answer. But again, if the assumption does work, it'll probably save you a little bit of time, obviously, along the way. Yeah. No, it's actually the K value. And the reason for that is because the K value is small, what that means is when we reach equilibrium, we mainly will have reactants. And because we'll mainly have reactants at equilibrium, that means any change that sort of occurred is going to be relatively small. And that's why we could assume it's going to be 0. We can't do that when we have a K value that's large, because that means when we reach equilibrium, we should mainly have products, which means the change from reactants to products should be relatively significant at that point. Other questions? Okay. So again, hopefully you can see Ka problem pretty much very similar to obviously regular equilibrium problems, except that you have the additional sort of step in most cases to calculate the actual pH. So the next thing we're going to talk about in terms of weak acids is what is sometimes referred to as percent ionization. You could also do it really for bases as well. But percent ionization is the ionized acid concentration at equilibrium divided by the initial concentration of the acid times 100. It is really the way that we check our assumption. So it's really what we just did there to check our assumption. You basically take the H plus concentration divided by the initial concentration, and you times it by 100. And in a strong acid, it is 100% ionized or dissociated. So it's going to completely break apart. In a weak acid, it's a little different. We have a lot more percent ionization here versus here. The difference between those two locations on this graph, between say here and here, the difference is the concentration. So we talked a little bit about it probably last time. Again, if you have a much smaller concentration to begin with, any type of change that you have is going to be a lot more significant than if you started with a larger concentration. The amount of change is going to be a lot less. So I think I maybe did the pizza example the other day. Again, if you had a whole pizza, I took one slice out, not a big deal. But if you were down to just 2 slices, somebody took one, right? You're now taking basically 50% of what you started with. So it's a much bigger percentage that's going to happen. So it's the same idea with concentration. And that's also what we saw in those 2 examples that we started with. It was the same acid, but the initial concentration of the first guy was 0.5. The assumption was all good. But when we drop that concentration from 0.5 to 0.05, which is much smaller, your assumption was no longer valid, and it was like 11% or 12%, right, at that point. So the initial concentration of the acid has an effect, obviously, on the percent ionization. And again, the smaller the concentration to start with, the higher the percent ionization as you see it. So let's take a look at a question here where we could kind of use percent ionization to help us figure out certain things. So we have a solution of formic acid. It is 0.47% ionized. What is the Ka value for the formic acid? So in this particular problem, we're actually looking to solve for the Ka value. So we can approach it like a normal sort of problem, which we know we have a Ka value. So we definitely know that this formic acid is a weak acid. So if we kind of set up the equilibrium here, we would have H plus and HCOO minus in this case. Our Ka expression would be our products divided by our reactants. And if we actually did an ice table here with the information given to us, we are starting with 8 molar of this guy, 0 of this guy. Change would be minus X plus X plus X. And if we got to equilibrium, we would have 8 minus X, X, and X. So if we kind of roll through this problem, kind of like normal, we get a very similar sort of ice table. And now normally what we would do, right, is we would stick those X squared divided by 8 minus X equals our Ka value. The problem, though, is that is what we are looking for, right? So we need to kind of look at the other piece of information that was given to us, and that is where the percent ionization could come into handy here. We are told that it is 0.47% ionized. So as we just saw on the previous slide, percent ionization is equal to the H plus concentration divided by the initial concentration of the acid times 100%. So in this particular case, we have the percent ionization at 0.47% equals the H plus concentration 100%. We could use the percent ionization here to calculate the H plus concentration. And if we did that, the H plus concentration in this case would be, we would take 0.47 times it by 8 divided by 100 will give us 0.0376 molar. First off, any question on what I've done so far? So using our percent ionization, we're able to figure out the H plus concentration. That would be important in this case because if we go to our ice table, we can see that the H plus concentration at equilibrium basically equals X. And that X value is this X value because it is the same. And it is also that X value as well. So by using the percent ionization, we're able to figure out what the concentration of H plus is at equilibrium and actually allow us to get numbers for each of these things. So we know that that's the H plus concentration. That would also be the concentration of our formate and our formic acid concentration, as we can see from our ice table, is 8 minus X, which in this case is 0.0376. Gets us something like, we'll call it 7.96 molar. Now we have everybody that we need. We now have this guy's concentration equilibrium, this one, and this one's concentration at equilibrium. That's going to allow us now to put all those numbers into our Ka expression and get an actual number. And if we do that, our Ka would equal basically 0.0376 squared divided by 7.9624. And that's going to give us 0.0376 squared divided by 7.9624. Going to give us a Ka value of 1.8 times 10 1, 2, 3, minus 4, looks like. In this case. So by using the percent ionization, we could kind of back calculate, if you will, to figure out our change that occurred. And also that allowed us, again, to really calculate the equilibrium concentrations of everybody that was there. Questions on that? Yeah. What we were doing before is we did have the Ka value given to us. So we were able to at this point actually go into here because we had that number originally and we could solve for X, right? But in this case, we don't have the Ka given to us. That's what we were looking for. So we needed to use, like, for example, the percent ionization here to basically sort of back calculate what the X value was. And that allowed us to get to everybody equilibrium. Yeah. And this would be, you know, kind of using percent ionization in that form. You could also just have sort of a straight percent ionization question where it asks you, you know, what is the percent ionization of this acid? And you just need to figure out, you know, the H plus concentration and all that, and based on the initial one. You could actually do a problem like we were doing and get the X value and using, however, the quadratic your assumption, and then just stick it into the percent ionization at that point. Other questions? Okay. Now, we've talked about weak acids, but weak bases actually work very similar to how we approach weak acid problems. Because they are weak bases, they will set up an equilibrium. And remember that when you are writing the equation for a weak base, that's probably one place where you probably do want to include water in there. So maybe you could visualize that this guy is going to send over the H plus there, and we're going to make hydroxide. We would write a Kb value. Again, we know it's a Kb value because of that hydroxide. It is our products over our reactants. The Kb value, as it increases, so does the strength of a weak base. And clearly a weak base is nowhere as strong as a strong base. Remember that most of our strong bases come from group 1 and group 2 on the periodic table there. Sodium, potassium, calcium, strontium, barium, with hydroxide in the formula. The reason, again, that as the Kb value increases, so does the weak base increase, or the strength of it, is that the increasing K value means more products. More products means more hydroxide has been produced, and thus it is a stronger base in that case. How do we solve these problems? We do it exactly like how we do the weak acid problems, except obviously you need the proper equation, which is not an acid equation. And the difference is, though, when you get down to the equilibrium line of your ice table, you're going to have hydroxide. So typically when you solve for X, that is the hydroxide concentration, which means usually you will need to go to the POH first and then to the pH at that point. So that is a slight difference, and sometimes people just kind of gloss over that part of it. And also why it's really important to make sure you understand how to properly write these equations so that you do not write the wrong equation and see H plus on the right-hand side of the equation when you should see OH minus. So you do get the OH minus to the POH and then to the pH. You do all the same stuff. You can make the assumption if it works, or not make the assumption, whichever way you want to do it. But it's basically worked the same way. Any questions on that there? All right, so here is a table from your book of some weak bases and their Ka values, or Kb values, I'm sorry. So why don't we try one here? An amine compound has a Kb value of 5.6 times 10 to the minus 4. What is the pH of a 0.15 molar solution of this weak base? Take a few minutes there, see what you come up with. Have a Kb given to us. So even if they weren't nice enough to tell us this is a base, we should know it's a base, and that should help us write the equation that we need, which is our base here. And again, with bases, definitely weak bases, including water, is helpful. then really all you got to do is go by definition of a base, which is it's going to accept the H plus. So you're just going to send that H plus over there, and that will give you what you need, hopefully on the other side, which should be pretty much the exact same guy, except we're going to add an H plus there at the end. And obviously when water loses its H plus, it will produce hydroxide, which again is why this is a base. So definitely I would include the water in the weak base reactions and just follow the definition of a base, and that will hopefully get you to what you need in terms of the equation. Because this is a KB here, we'll write our KB expression would be our concentration of our product. Over our reactant. And again, this equals our KB value, which was 5.6 times 10 to the minus 4 in this case. Going into our ice table, which is the other thing that we should know, because it is obviously a weak base. We will start with our initial, which is 0.15, 0 and 0. Change here minus x plus x plus x. That means at equilibrium here, 0.15 minus x, x, and x. Any questions up to there? So again, here, we're just going to do our normal sort of process. We're going to put that into our KB expression here, and that will get us a x squared divided by 0.15 minus x equals 5.6 times 10 to the minus 4. You could assume that x is equal to 0. Is it a good assumption in this case? It is not. It's a bad assumption. It's above 6%, I think, as well. So once again here, double check that you do check your assumption. We're going to then solve it the other way, which is the quadratic. So that's going to require us to multiply what's on the bottom right to the other side, and if we do that, gets us an x squared is equal to 0.000084 minus 5.6 times 10 to the minus 4x. We're going to bring everybody to the same side. That means I'm going to bring everybody on this side over there to the left, and that's going to give me x squared plus a 5.6 times 10 to the minus 4x minus 0.000, not missing a 0, equals 0. That again is going to give us our A, B, and C here that we need for our quadratic. At this point here, we'll go x is equal to minus b, which in this case is minus 5.6 times 10 to the minus 4, plus or minus the square root. When you put all the numbers into the square root part, before you take the square root, 0.000336,314. We'll keep all the numbers, why not? We're going to take the square root of it, which will give us 0.018339. That's all going to be divided by 2a, which is basically 2 in this case. Going the plus root here, that will give us an x value of about 0.0088895. You could round it there a little bit if you want to at this point, or if you want the subtract root, it gets you a negative 0.00944495. Any questions on that there? Are you talking about when you write the equation? Yeah, so you always, well, I won't say, definitely with weak bases, you should add the water on the left-hand side always. Remember, you could also do that with weak acids, and the only difference would be you would get H3O plus on the right-hand side and rather than H plus. So you could do it with acids as well, but you definitely would do it here with probably the weak base. And then because you do know that this guy is a base, you could just follow the definition that it should accept it. And in that case, because it is a base, it should always produce hydroxide on this side, yeah? Otherwise, if it produced like H3O plus or H plus, then it's not really a base, right? So it's got to produce that hydroxide now. Other questions? Okay. So at this point, if we look back at our table, we can see that the hydroxide concentration actually is equal to X, which once again means here that negative value is not going to work for us because we cannot have a negative concentration. Also really important, again, as I mentioned a couple of times, to make sure that you do have the equation correct, because if you do, you will now clearly see that that X value is actually the hydroxide concentration and not the H plus or H3O plus concentration. So that's going to be 0.0088895. That allows you to go into the POH, which is an important distinction here. And that will get you a POH of about 2.05. Now, again, even if you've perhaps messed up writing the equation, but still can see in the problem that this is a base, and you thought maybe that was your pH value, it should not make sense, right? If that was your pH value, because that definitely is an acidic pH, that is why that is actually the POH value here, right? So again, there's a couple places where you can kind of check yourself in case maybe you wrongly think about it at some point. You want to make sure things make sense. So we do want to get to the pH here, and that would be our 14 minus our 2.05. And that's going to give us a pH, which will make sense in this case, of 11.95, which is definitely a basic pH, which is, again, what you would probably hope for there with a weak base, right? It's not giving you an acidic pH. Yeah. Question on any of those steps there? So again, it is very similar, obviously, to how you take care of weak acid problems. The major difference is that X value being the OH minus. Usually got to do that POH first and then to the pH. Yeah. I should say part of that. Okay. So let's talk a little bit about Ka and Kb, and sometimes people have a really sort of hard time maybe understanding or using each of those values and when you should use those values. So let's talk a little bit about that. So if you actually took the Ka value, which is what we have here, and if we took the Kb value, which is this generic equation, if you actually add the weak acid reaction to the weak base reaction, which is the Ka and the Kb sort of reaction, you get pretty much water here. So that cancels out, and you're left with really the formation of water, which we know is also a Kw value, right? Also an equilibrium constant. So there will be certain cases where you may be given the Ka value, but you really need the Kb value, and vice versa. You may be given the Kb value, but you really need the Ka value. So we know, hopefully, right, when we add these equations together, we multiply these K values to get there. And when you do that, it gives you this expression, which is if you take the Ka value times the Kb value, that will equal Kw, and that Kw is still the same in most cases 1 times 10 to the minus 14 value that we've used previously in this chapter. So the question becomes, again, how do I know maybe if I'm using the right one or which one I should use? There's a pretty dead-on way that you can figure out, which one you should be using. And it really boils down to writing the correct equation. And again, if you write the correct equation and you see H plus on the right-hand side of the arrow or H3O plus on the right-hand side of the arrow, that is definitely, you should be using a Ka value. If you write the proper equation or given the equation and you see hydroxide over here on that side of the arrow, that should be Kb territory. Yeah. So you want to make sure you have those equations, and that's pretty much how you know you should be using that. Also, how you know in most cases, probably, if you have H plus or H3O plus there on the product side, probably going to be more of an acidic solution. And if you have OH minus there on the product side, going to be more of a basic solution. So these are the things that sometimes people kind of overlook and they just kind of go on autopilot. trying to fake the math, if you will, which not really understanding what's going on. And again, they'll use the wrong K value. So when we talk about salts, this is very common where that occurs. And a lot of times hydrolysis type problems, they will give you, again, really the wrong K value and stuff like that. Any questions on that there? Okay. So let's talk a little bit also about acid strength. So there's really kind of two types of acids. There's acids that obviously contain oxygen, and then there's acids that do not contain oxygen. And if you're comparing the acid strength of acids that actually do not contain oxygen, there's really a couple of things that, we really want to focus in on in that comparison. And it may not be what you think. So you may think that maybe we would look at the electronegativity values. And in the case actually of acids that do not contain oxygen, the overwhelmingly thing that we look at is what is known as bond enthalpy. And maybe you remember that from previous semester when you talked about probably bonding, I'm assuming. You add up all the bonds you break, add up all the energy of the bonds you make, right? And add them together and get the right amount of energy. So bond energy or bond enthalpy is the energy required to really break a bond. And when we look at, say, group 7 there, we see that HF has the highest, I kind of scrolled over there, has the highest bond energy on the list there. And we actually see bond energy starts to decrease as you go down group 7. So why that's important, for example, is if I have HF versus HI, which bond is easier to break? It is the HI. It takes a lot less energy to break that bond versus this bond here in HF. That's important because pretty much the definition of an acid is the ability to produce H+, which means in order to produce H+, you got to break that bond, right? So because the bond energy is a lot less with HI, it's a much stronger acid than HF, which takes a lot more energy to break it, which means not as much of that H plus is going to come off in the case of HF versus HI. So if we were looking at sort of group 7 acids, if you will, HF is a weak acid, and then the other 3 are considered strong acids based on what we talked about: hydrochloric acid, hydrobromic acid, and hydriodic acid. Actually is a lot stronger of an acid there than, say, hydrochloric acid, even though we always think of hydrochloric acid a lot as like a strong acid. But HI is actually a little bit stronger. Now, when we deal with, and here's a table from your book that also illustrates that, again, acid strength increases as you go down and to the right, and base strength goes the opposite ways, basically. Remember that acid strength and its partner base are opposites of each other, right? So if you have like a strong acid, a weak conjugate base, and vice versa. So that's why they kind of run opposites of each other there on that table. When we do deal with acids that do contain oxygen, they are sometimes called oxyacids because they do contain oxygen. We really have to look at one of two things depending on the situation in terms of comparison. We can either look at the electronegativity, or we could look at the oxidation state or number. A reminder, electronegativity, right, is the ability of an atom to bring electrons towards itself. Increases as you go up and to the right, right? On the periodic table, with fluorine being the most electronegative, decreases as you go down and to the left on the periodic table. Oxidation state, as you might remember from some redox stuff you maybe talked about, and we'll talk more about in a later chapter, is really the sort of charge that an element takes, oftentimes in a situation where they are sharing electrons. So oxidation state is not necessarily always the charge that you may associate with an element when it's in an ionic compound, because in an ionic compound, we have a full transfer of electrons from the metal to the non-metal, which means it gains a normal sort of charge. In a sharing of electron situation, elements that we normally think about as having negative charges could end up with a positive oxidation state because of the way they're sharing electrons and who they are bonded to in that situation. So Z is very electronegative, or if the central atom there has a high oxidation state, that would create a much stronger sort of acid. So let's take a look at a couple of those sort of situations. So we have two acids here, and this is an oxyacid that has a different central atom, but has the same oxidation number. So again, here to assign oxidation numbers, oxygen in most cases is -2. So this would be -2. This oxygen would be -2. This oxygen would be -2. And hydrogen in most cases has an oxidation state of +1. If we add up all those negative oxidation states, that's -2, -2, -2 is -6. The hydrogen is +1. Oxidation state should add up to the same charge as the molecule. In this case, it's neutral, which means in this case, the chlorine is carrying a +5 oxidation state. If you have a +5 and a +1, that's +6, and -6 is 0. So everything adds up to 0. We do it for the guy on the right. Oxidation state of this guy is -2, -2, -2, and +1. Once again, here, the bromine would actually carry a +5 oxidation state in this case. Again, normally, right, in an ionic situation, we think of Cl and Br as having a -1 charge. And that is true when it is an ionic compound and it gained all those electrons. In this case, it is actually sharing electrons with both oxygens, barely oxygens in all these cases here. So it takes on a more positive sort of charge, because in probably each of those cases, oxygen is a little bit more electronegative, which means it's going to be sucking those electrons towards the oxygens, making the central chlorine and bromine more positive, more electron deficient, which is why it ends up with a more positive charge in this situation. So in this particular situation, we cannot use oxidation state of the central atom because, frankly, it's the same. So, right, so there is no difference between them. So in this case, when we have the same oxidation state of the central atom, we actually need to look at electronegativity. And in this particular case, between chlorine and bromine, the more electronegative atom is Cl, right? It is further up in the group. And what that means is this, right? We're really talking about this bond right here. That is where our H plus is going to come from, right? When it's an acid, so that's the H is going to pop off there. By the way, the OH bond, is it polar or non-polar, that bond to begin with? It is a polar bond, yes. The difference in electronegativity between hydrogen and oxygen. Oxygen's a little bit more negative, right? Hydrogen's a little bit more positive, I believe is what they say. That also goes for this guy over here. That means the electrons are actually closer at this point towards the oxygen, right? Because it's more electronegative, which means if we have our chlorine here, which is also more electronegative, those electrons are going in and they're going to be kind of brought in closer to the chlorine as well. What that's going to do is weaken this bond, right? And allow that H basically to pop off a lot easier, as opposed to here where it is still coming this way, not as big of a pull from the bromine in comparison to the chlorine. So it's going to be a little bit harder to pop that one off in a comparison of the two. That means in this case, because chlorine is more electronegative, that guy right there would be the stronger acid of the bunch there. That's chloric acid versus bromic acid in this particular case. Question on that there. All right, so in this case, when we have the same oxidation state on the central atom, we should look at electronegativity. Now, if we have a oxyacids where we do have the same central atom, but different groups attach, what that means is we cannot look at electronegativity of the central atom because they're all the same, but we do have to look actually at oxidation number. So if we were to assign oxidation numbers for each of these guys, once again, starting with the oxygen, that would be -2. This would be +1 for the hydrogen. That's going to give us, to get to 0, a +1 for the chlorine in that case. For the guy to the right there, it's going to be a -2 for that oxygen, -2 for that oxygen is -4. a +1 for the hydrogen. That is a -3. So to balance that out, that's going to be a +3 charge, our oxidation state there on the chlorine. This is the one we just did, -2, -2, -2, +1, giving us a +5 in this case. And here, this would be -2, -2, -2, -2, and +1. That's a -8, and a +1 means that this chlorine here has a +7 charge. Yeah. So the idea here is the same. It is that HO bond there that's going to release that hydrogen, ready polar as we just discussed. So now that we have a central atom that has a much larger positive charge, that's going to attract those electrons in even more. And again, weaken that bond a lot easier to allow the H+ to come off. That means the strongest acid out of this bunch should be perchloric acid with the +7, because it's going to really weaken that bond, followed by this guy would be the next. So if you have an oxy acid that basically has the same central atom, again, electronegativity is not going to do you much because they're the same atom. So you can't use that to define it. You want to look at oxidation number to help you to decide which one would be the strongest. Any questions on that? Yeah. It's the strongest acid in that group. And again, it's because of, once again, that bond, and that is the hydrogen is going to come off. It's already polar to begin with, which means pretty much the electrons are hanging out near the oxygen. So when you have something like a +7 there in the central atom, that opposites attract, right? So that's going to kind of bring those electrons even kind of closer into the center. And what that's really going to do is really kind of weaken this bond a lot more and make it a lot easier for this guy to come off and basically release that H+. In comparison to this guy, where instead of a +7 in the middle, you only got a +1 charge. So it's not going to be as big of a pull, bringing them even closer to the center. And then it would be a weaker acid in comparison to the first one. Other questions? All right. I think that's enough torture for today. We'll lay it up there.